Well, hello everybody. Dave here today to finish up our lessons on fluids with this idea of fluid dynamics. Previously, we dealt with fluids in the case where they were static inside some container, and we dealt with things like buoyancy. Now we're actually going to have the fluid move and try and understand the motion associated with that. You can see on the front screen here that we have this picture of these green lines going over this car, and you see that mess at the back of the car. Well, this is actually an exhibition of fluid motion over the car in this concept of aerodynamics, and it is one of those activities that scientists use to determine just how much drag is associated, and based on that, how can they improve the design of the car to improve things like fuel economy. If you look at any studies about race cars, you will see that this concept of aerodynamics and fluid motion over top of the car is absolutely essential. So as we begin our discussion of fluid flow, I'd like to remind you that a fluid by definition is any material that is unable to withstand a static shear stress. What that means is as opposed to something like a solid, which can be deformed and then recover from that, when we apply a force to a fluid, it will inevitably take the shape of whatever container it's in. We define fluids according to two types of state of matter. We have liquids or gases, but remember that when we talk about the difference between the two, a liquid has a defined volume, which means that when you change the container that a liquid is in, you don't actually get to contain that entire volume. Whatever volume of liquid existed will be the volume in the new container, unlike a gas that will actually take the shape and volume of whatever container it's in. So with that definition, we are going to make assumptions based upon the idea of an ideal fluid. So the first assumption is that the fluid is itself non-viscous. And what that means is fluids can actually be layered, to which there is an internal friction between these layers. We are going to make the assumption that there is no internal friction so that this layering doesn't affect the overall energy state of the fluid. The second, and one of the most important assumptions, is that the fluid is incompressible. And what we mean by that is that the density is going to remain constant. And as we see, when we track the fluid through its motion through a pipe, this incompressible nature is going to allow us to make some calculations based upon the overall volume and mass of the fluid there. The third assumption is that the motion is actually going to be steady state. And what we mean by that is that it will be in what's called laminar flow. And so laminar flow, again, is this idea that all the particles within the fluid is going to move in the same path as the one before it, unlike turbulent flow, where there could be this chaotic nature associated with the motion after the fact. If you take a look at the front page again, the back of that car is an example of what turbulent flow looks like, that there is this chaotic sort of event occurring, which can be studied, but for the sake of this course, we're not going to deal with that. So a streamlined flow, or this idea of laminar flow, is going to be essential. You can think of a garden hose and water leaving that, where all of the water is going to leave in the same direction and is going to follow the exact same path as the one before it. So these particular assumptions are absolutely essential in what we're going to do next. So let's look at a small section of pipe and put some liquid through it. Now again, we are assuming that the liquid is constant density and incompressible. And if we want to find the volume of a small section of that liquid, then we're looking at the case of a cylinder. So if we want to find the volume of this cylinder, we have the area of the base times the height, which is defined as A delta L. But we also know that there's no statement about acceleration, which means that we are dealing with a constant velocity case. We know that constant velocity is equal to distance over time. The distance traveled is this change in length. The time is delta t. So we can actually define the length according to the velocity of the fluid times this time. Well, if we substitute that in for delta L, now we have an equation that shows you the change in velocity in terms of the cross-sectional area, the velocity of the fluid, and the time that it takes. If we solved this for delta V over delta T, what we would now have is this thing called the flow rate. But we want to take it one step further. And so what we do is we substitute in for delta V density and mass. Remember that density is equal to mass per unit volume. We have assumed that the density of this fluid is constant, so when we take a look at the left-hand side now, we see that the mass divided by delta T is equal to AV rho. And what we call this is the mass flow rate. So the first flow rate at the beginning, delta V over delta T, is the classic definition of flow. but now what we're doing is we're substituting in for delta V to get what this mass flow rate is. Again, you should be able to do both. So let's take a look at a question like what happens if the area changes. So we have our original pipe with a cross-sectional area of A1, but what we're going to do is we're going to change it into a new pipe with a different cross-sectional area. Now it doesn't have to be smaller, it could be larger, but the point that we're trying to make here is that we aren't destroying, we're not creating, we are actually conserving mass as is law. So when that's the case, whatever the volume of liquid is in the first pipe has to be the same volume of liquid in the new pipe with the new cross-sectional area. And so if we take a look at our mass flow equation, we can see that our change in mass in the first pipe is simply equal to all the values associated with that pipe, the velocity, the density, the cross-sectional area, and the time that it flows. Well, if we take a look at the second pipe, we can see that the change in mass there is going to be all the values associated with that pipe. However, we know by definition that the mass in the first pipe has to be the same amount of mass in the second pipe, so we can make that equality to give us the equation with our various cross-sectional areas and velocities. However, we also know that we are making the assumption that the density remains constant. Because of that, density will cancel out. The time that it flows is going to be constant, which means that we actually result in the equation of A1V1 is equal to A2V2. Well, this, my friends, is something called the continuity equation, and it is something that we will use excessively in fluids, so I highly recommend that one, you understand what flow rate is, how we related it to the mass flow rate, and how both of those relate to this idea of the continuity equation. So let's use this in an example, and I'm not a big biology fan, but let's be honest, there's a lot of fluid flow in our bodies. So the speed of blood in the aorta is 50 centimeters per second, and this vessel has a radius of 1 centimeter. If the capillaries have a total cross-sectional area of 3,000 centimeters squared, what is the speed of the blood in them? So again, it's important to recognize first and foremost that we have a unit concern. We see that our speed is in centimeters per second, we have a radius that's in centimeters, and we have a cross-sectional area in centimeters squared. What I see is the units are all in terms of centimeter, but as long as we recognize that when we have our final answer for V, then we can see that the answer is going to be in centimeters per second. The typical method, of course, would be to convert this into meters and meters squared, but then we're going to end up with some really small numbers. You can see already that the speed at which the blood flows through these capillaries is really quite low, and so if we had this in meters, it would be an even smaller number. It's not that it's wrong, but you're more than welcome to leave it in centimeters in this case. You'll also notice that when we found the cross-sectional area, we have assumed, of course, that it is circular in nature. This will almost always be the case, as the majority of pipes are circular, but keep in mind that it could be any shape of pipe by which we can calculate the cross-sectional area. And with that, we move to the most important concept of this lesson with Bernoulli's principle. And the thing I want to start off with is just a disclaimer that Bernoulli's principle is not in itself a freestanding law in physics. It is actually a great example of the conservation of energy. And what you'll see through our derivation of Bernoulli's equation is that we will go back to fundamental principles associated with energy and its conservation and how they apply. But the concept of Bernoulli's principle states that if the velocity of a fluid increases, the pressure decreases and vice versa. And so I'm giving you two examples on the screen here. The first one on the left is known as a Venturi tube. And what this is a larger cross-sectional area, a horizontal pipe that leads to a narrow cross-sectional area. And what happens is the velocity of the fluid will actually increase through the narrower section, but what we found out is that the pressure will actually decrease as a result. And so this is actually a great way to measure the velocity of a fluid if we understand Bernoulli's principle and how the velocity plays a role in this pressure differential. The picture on the right, of course, is a wing of an airplane, and it is the basic concept that allows us to fly. And it's this differential pressure between the top of the wing and the bottom of the wing that allows this overall force of lift to occur, which keeps the plane in the air. I used to be really afraid of flying before I understood this concept here. You'll notice that the shape of the wing is not necessarily a rectangle, it's actually something called a foil. And it is this shape alone that allows the fluid to have to travel faster above the wing instead of below the wing, because the fluid has to get to the same point of the wing at the end. Well, to do so, the fluid above the wing has to travel faster or else it won't make it in time. Because of that, the fluid or the air above the wing is traveling faster than the air below it, and the result, of course, is this lift. So fear not, my friends, these planes are being governed by the laws of physics. So to derive our Bernoullis equation, we start with a scenario that looks like this, where we have a pipe with ends at two different heights with two different cross-sectional areas. And the first thing we have to figure out is how much work is being done by the water column at the bottom to the water column at the top. And so we remember from previous exposure to energy that work is equal to the force applied times the distance traveled. So in our case, we can apply our pressure equation to get an equation for force, which we can substitute in, so that we get a work equal to pressure 1 times A1 times delta x1. We also know that the cross-sectional area times the length traveled is actually equivalent to the volume of the fluid itself. So we end up with an equation of work 1 is equal to P1 times V. Similar ideas go into the work being done on the column at the top. Obviously, because the work's being done on it, we end up with a negative work scenario to end up with our equation of negative P2 times V. That gives us a work being done by the fluid equivalent to P1 times V minus P2 times V. Now this work is actually responsible for two different things. Part one is that it actually has to change the kinetic energy associated. Remember that if we have a cross-sectional area change, then there is also a fluid speed change as well. So our change in kinetic energy is going to be the difference in kinetic energy at the top and bottom. At the same time, because there's a change in height, there's also a change in gravitational potential energy, which is given by our classic equation dealing with mgh. So if we combine these two ideas together, we have the work of the fluid being done from our previous derivation, which is P1V minus P2V, and then we have that the work of the fluid is also equivalent to whatever change in kinetic energy exists and whatever change in potential energy exists to get this equation right here. Now we can do something tricky. We can divide both sides by V, and what we'll end up with is a bunch of mass divided by volume expressions on the right hand side. Well, we know from previous exposure that that's actually equal to the density of the fluid, and so we can substitute that in as you see. If we rearrange this equation now in terms of the bottom part of the tube and the top part of the tube, what we get here is what's so affectionately known as Bernoullis equation. And if you look at this, there's something really important to recognize here, that what we're dealing with is the initial pressure associated with the fluid, the kinetic energy of that fluid, and the potential energy of that fluid, and then the final conditions on the right. If we let V equal 0, what we end up with is our equation for hydrostatic pressure that we figured out in the last lesson. So this is an interesting consequence of Bernoullis equation, is it actually has all of fluids wrapped up into one. And if we think about it a different way, we can make the statement that P plus 1/2 rho V squared plus rho Gy is equal to a constant. And what that means is that the conservation of energy still holds true, and that anywhere along the fluid's path, the sum of the pressure, kinetic energy, and potential energy all have to have the same value no matter where you are. So as an example, let's deal with a situation like this, where we have water circulating a house in a hot water heating system. If the water is pumped at a speed of 0.5 meters per second through a 4-centimeter diameter pipe in the basement under a pressure of 3 atmospheres, what will the flow speed and pressure in a 2.6-centimeter diameter pipe on the second floor 5 meters above be? We have to start off with the first idea, which is determine what the speed of the water is in the smaller pipe. So again, we have a unit issue that we have to consider. We have the initial speed of 0.5 meters per second, but we have this diameter in centimeters, so we have to convert that into meters. But when we do so, what we find out is that the speed of the water in this new pipe is actually 1.183 meters per second. You'll notice that in this case, we now have to deal with this conversion from atmospheres to pascals. And so as a reminder, 1 atmosphere is equal to 1 times 10 to the 5 pascals. So given the information that we have, we can substitute into Bernoulli's equation. We have the initial pressure, we have the kinetic energy, and we know that the initial height is going to be defined as 0. How can we do that? Because again, we're dealing with potential energy, and we can always establish the 0 potential line. So we know that our change in height is going to be 5 meters. So on the right-hand side, we don't know what the pressure is going to be, but we do know the kinetic energy because we have the speed of the fluid, and we know the potential energy because we have the height relative to 0. And that gives us a final pressure of 2.5 times 10 to the 5 pascals. So recognize the fact that we're playing around with different units of pressure, but at the same time, everything that we've learned in this lesson now becomes applicable. So everybody, that's Bernoulli, that's continuity, that is the basics of fluid dynamics. So good luck with your example problems, and we'll see you again.